These are the solutions to homework set number 8 for EE206. On the first problem, I want to convert voltages for AC. At DC, you just have a number to represent a voltage. AC, there's three ways to represent a voltage. I can do the peak to peak, and RMS. The relationship is the peak to peak is twice the peak voltage. The RMS voltage is the peak divided by square root of 2. So 15 volts peak means 30 volts RMS, or 15 divided by square root of 2, 10 volts RMS. 7.5 volts peak is 15 volts peak to peak, or 5.3 volts RMS. 15 volts RMS is actually 21 volts peak, 42 volts peak to peak. The difference is, in the lab, if you measure the AC voltage, the voltmeters give you RMS voltage. The oscilloscope typically gives you peak to peak. And when you write the equation, you usually use the peak. Each of these has its own use, and they're all related. Problem 2 looks at how to solve this differential equation, a pretty common problem in electronics, or in electrical engineering. I have a differential equation where the input is a sine wave, find the output. The approach that you use in calculus is guess the answer. I'm going to guess the answers in the form of a cosine 5t plus b sine of 5t, and substitute. X goes in for x, y goes in for y. dy dt is I'll take the derivative. Derivative of cosine is minus sine. Derivative of sine is cosine. So there's the derivative. Plug it in. And now solve. The cosine terms have to match, and the sine terms have to match. That means that minus 5a plus 3b is 0, and 5b plus 3a is 2. Two equations, two unknowns, solve, and I get 0.17 and 0.29, meaning the forced response of that differential equation is 0.17 cosine 5t plus 0.29 sine 5t. And nothing got a minus sign. Yep. Oh, that's correct, 0.29 sine 5t. Moral is, if you don't use complex numbers, you get two equations and two unknowns, one for sine, one for cosine. If you were to use complex numbers, I can just have one equation, one unknown. And I much prefer one equation, one unknown. That's one of the main reasons we use complex numbers so much in electrical engineering. Third one, this is where you get to show off your calculator. If you have an HP calculator, this isn't hard. I just do a plus j3 divided by 2 plus j7 plus 4 minus j3 over a plus j5, and you get an answer. Part B is pretty easy on an HP calculator. It's just adding complex numbers, multiplying, dividing complex numbers. And problem 3 is really the same thing. Moral of this, if your calculator is struggling with problem 3, you need a new calculator. I would recommend the HPs. They handle complex numbers very, very well. On problem 4, if I see this in the lab, I want to represent x and y as a phasor. I need two parameters, the frequency and the phasor representation. The frequency is 1 over the period. Take the period, say peak to peak, 0 crossing for falling edge to 0 crossing falling edge. The period is 4 milliseconds. 1 over the period is the frequency, 250 hertz, or 250 cycles per second. If you like radians per second, omega is 2 pi f, so it's 500 pi radians per second, both for x and y. The phasor representation of x, the amplitude is the peak, it's about 4.8. The phase is this delay. One cycle is 4 milliseconds. The delay is about 1.8 milliseconds. Cosine is a peak at t equals 0. This is a peak at t equals 1.8 seconds, 1.8 milliseconds. So the phase is 1.8 milliseconds, that percentage of the period. One period is 360 degrees, so it's about minus 162 degrees. So x is 5.8 to minus 162 degrees. That's the phasor representation for x. Phasor representation for y. The amplitude is about 8.8. The delay is 0.7 milliseconds. So it's 0.7 out of 4. That percentage of the period. One period is 360 degrees, or minus 63 degrees. So y is 8.8 to minus 63 degrees. Problem 5. I can represent sines and cosines in phasor notation. The real part is cosine, minus j is sine. So 6 cosine minus 7 sine as the phasor representation of 6 plus j7. Note that the frequency doesn't appear in the phasor. The assumption is that everything in the circuit is the same frequency. If the input is 10 radians per second, everything else is 10 radians per second. So likewise, I don't need to write down the 10. It's understood. What does change is the amplitude and the sine and cosine part. That's what I write down in phasor notation. For problem 2, this would be 2 at minus 30 degrees plus 5 at 15 degrees. Again, if you have a calculator that does complex numbers, add them up and get a complex number. If you have a calculator that doesn't do complex numbers, get one. The third one is 7 at minus 20 degrees plus 9 at 0 degrees. Sine is minus j. Add these together, I get 6.5 minus j11. And the last one is, if this is a filter, x is the input, y is the output, what's the relationship between x and y? That again is a complex number. The amplitude is the ratio. The input is 2.8, the output is 4.4, the ratio is the gain. There it is, 1.536. The time delay is the phase shift. Y is delayed from x by about 5 milliseconds. 5 milliseconds with a period of 20 milliseconds is that percentage of a period. One period is 360, so the phase shift is minus 90 degrees. So this filter, the way to model it is the output is 1.5 times the input shifted by minus 90 degrees, where the phasor representation or gain is 1.5 at minus 90 degrees. That's homework number 8.